Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Superconducting Thin Films from the paper Thin Film Science and Technology. So students, let us see what we are going to learn in this module. Firstly, in this module, the superconducting behavior is discussed in contrast to normal metals. Then, the various properties of superconducting thin films are studied. Phenomenological and microscopic phenomenological theories of superconductivity, that is London theory and Ginzburg-Landau theory, are explained. Microscopic theory, that is the BCS theory of superconductivity, and BCS many particle state theories are discussed. The important terms related to superconductivity such as electron-phonon interaction, Cooper pair, and Josephson effect are studied. H. Kamerlingh-Onnes in 1908 measured the electrical resistance of metals at very low temperatures. He did this by successfully liquefied helium. In 1911, scientists discovered that as the temperature of mercury was reduced at around 4.2 Kelvin, the resistance of mercury did not fall continuously as expected, but in its place it dropped suddenly to zero over a range of a few hundredths of a degree. This phenomena of non-zero resistance of a metal was termed as superconductivity. Later on, the same phenomena was also discovered for other metal elements such as lead, tin, and aluminium at critical temperatures lying between 4 to 10 Kelvin. However, the microscopic mechanism of such an unexpected behavior of the metals found at some critical temperatures known as superconductivity was not discovered until 1957. In 1957, three of the scientists, Bardeen, Cooper, and Schrieffer, tried to investigate the microscopic behavior. In 1933, Meissner and Oschenfeld was also discovered one another important property of superconductors called the Meissner effect. Superconductors exhibit the property of perfect conductivity, such that the magnetic flux should be excluded from entering a superconductor as shown in the figure, whereas it is also found that when the superconducting material was cooled through its transition temperature, the magnetic flux was expelled from the interior of the material. This phenomena is known as Meissner effect, which is shown in the figure. As compared to the bulk materials, the superconducting properties of thin films are found to be much more different and superior. The superconducting transition temperature Tc of thin films changes remarkably with the film thickness. Thus, it can certainly affect the superconducting behavior of the deposited material. In the nanometer scale, range of the film thickness, the motions of the electrons of the film surface and boundary is confined and leading to the formation of isolated electronic states called quantum well states. The overall electronic structure of the film changes due to the quantum size effect. Also, the physical properties of the films vary considerably at small thicknesses. The latest investigations have also demonstrated the variations of the properties of deposited films with film thickness, such as the electronic density of shades, electron-phonon coupling, surface energy, and thermal stability. Let us now discuss the effect of superconducting behavior on different properties. Firstly, because of the superconducting behavior, the material exhibits infinite conductivity. Second important thing is the Meissner effect. Thirdly, the critical field Hc, below which the material is superconducting and above which it becomes normal. Fourth, the property of persistent current and flux quantization arises because of the superconducting behavior. Fifth, the variation of specific heat with temperature changes at abnormally at the critical temperature Tc. Last one is the isotope effect, which is seen in superconducting thin films where the transition temperature Tc varies with the ionic mass m. That is, Tc is proportional to 1 by square root of m. The four-mentioned superconducting features of the materials are discussed in the coming slides. Let us now discuss the distinct behaviors exhibited by superconducting thin films. The first one is the zero resistance or infinite conductivity. Below a specific temperature called critical temperature, which is also known by the symbol Tc, the electric resistance suddenly falls to zero in a superconducting material. The perfect conduction of the current will be achieved at zero resistance. Although it does not happen in reality due to the defects and vibrations of the atoms, which causes the resistance in the material when the electrons flow through it. However, after all such defects and vibrations, existence in a superconductor, the electrical resistance is equal to zero. Second is the property of persistent currents. Persistent current is the current which is set up in a semiconductor forever. That is, without any driving voltage, a current will flow forever in the superconductors. As a consequence, magnetic flux that passes through a continuous loop of superconducting materials remains constant as shown in the figure. That is, even when the specimen is cooled below its critical temperature in an applied field B0, the value of flux is maintained through the specimen even when the applied magnetic field is removed. Another important property of superconductors is of perfect diamagnetism. In atomic orbitals, the current is induced by the application of an applied magnetic field which causes diamagnetism. The applied field is opposed by the diamagnetic material and the induced currents produce a magnetization within the material. Also, in the absence of applied field, the induced magnetization disappears. The relation of the magnetic field in diamagnetic materials is given as B is equal to mu naught H. Here, the relative permeability mu is slightly less than unity. In a superconductor, the field B is zero in the interior. That is, The field is completely screened from the interior of the material. This is the extreme consequence of the diamagnetic effect in the superconductors. Hence, in superconductors, the relative permeability is zero, and the same is illustrated in the figure. Another important property of superconductors is the energy gap. The energy spectrum of the superconducting materials is found to have the gap in it. That is, there is an existence energy interval with no allowed eigenenergies in this region. The evidence of this phenomena is lying in the fact that the most thermodynamic properties of a superconducting material are found to vary as e raised to power minus delta by kBt. Thus, the unoccupied states above the gap can be filled by the exponentially smaller number of particles which have enough thermal energy equal to the energy of gap. When the energy of the external magnetic field is equal to the energy gap of the superconductor, electrons in the superconducting state are able to absorb in this energy and bridge the energy gap to a normal conducting state, resulting in a dissipative resistance initiated quench for the superconductor. Let us now discuss the various theories of superconductivity. We will first start with the phenomenological theories. Basic theory is the London theory. A phenomenological theory by assuming the essentiality of the diamagnetism and describing the electromagnetic properties is proposed by London. The theory assumed that there is somehow a consistency or stiffness in the superconducting state, such that in the presence of magnetic field, the wave functions are not modified very much. This kind of approach is suggested by F. London and is known as a quantum theoretic approach. The presented theory gives a two-fluid picture, namely the electrons from a normal fluid of concentration and a superfluid of concentration. London suggests some equations based on the defined theory which permits the absence of magnetic field inside the material. The equation is del cross J is equal to minus of NSE square by MC into B. Another phenomenological theory is the Ginzburg-Landau theory. Landau theory describes the second order phase transitions with symmetry reduction of the materials. It says that there is a thermodynamic parameter which takes zero value in the symmetric phase, which is occurring at high temperatures, and in the less symmetric phase it becomes non-zero continuously. Superconductors are categorized by the free energy density parameter R, which vanishes above the Curie temperature Tc. Non-uniform field superconductors, effects of surface, quantization of flux, and type II superconductors are described successfully by Landau's theory. There are some unanswered questions after the phenomenological theories. The phenomenological theories successfully described the various phenomena related to the superconducting state of the material and are well established, but the major mechanism of microscopic features of the superconductor are still unquestioned. A large category of the physicists working in 1900s attempt to answer this question. Some of those are Bohr, Einstein, Feynman, Born, and Heisenberg. However, in 1957, Barden, Cooper, and Schrieffer give a significant contribution to this with the famous theory called the BCS theory. Their theory came around 50 years of the experimental discovery by Kamerlingh Onnes. The discontinuity in the energy spectrum of the superconductors is appeared as a consequence of the exponential decay of the specific heat at low temperatures. Since an electron-hole pair excitation in case of metal near the Fermi surface requires very little energy, which contributes to the continuous spectrum of the metal and found to be in contrast to the superconducting materials. The isotope effect is found to be another major experiment. If capital M is the mass of the isotope, then from the fundamental study of the superconducting materials containing different isotopes, it is observed that Tc follows the relation m to the power minus 1 by 2, where Tc is the transition temperature of the superconductors. Since mass m is connected to the ions forming the lattice, therefore this study suggests that the lattice and hence the phonons play a crucial role in the structure of the superconducting state. The attractive interaction between the electron-electron or electron phonons generate Cooper pairs, that is, bound states formed by two electrons of opposite spins and momenta. It is considered as the key parameter of the BCS theory. The discontinuous energy spectrum and perfect diamagnetism of the superconductors is presented by the macroscopic ground state formed by Cooper pairs. The existence of a well-defined Fermi surface is considered as the main feature of the formation of Cooper pairs. Before describing the microscopic BCS theory, understanding of some terms is important. The terms are as follows. First one is the electron-phonon interaction, an effective attraction between conduction electrons gives rise to the superconductivity. When the two electrons are placed in a metallic environment, there exists additional attractive forces between the electrons with the repulsive Coulomb force. This attractive force, in case of standard superconductors, arises due to the interaction with the ionic system. In case of a normal metal, homogeneous positive background of ions is considered, which generates charge neutrality in the system. This is the polarized medium. An electron lying close to the Fermi surface moves with a much larger velocity than the velocity of the ions. Hence, during the process of polarization of the ions, that is, time period is of the order of 10 raised to the power minus 13 seconds, first electron covers a distance of approximately 100 angstrom. While before the ionic fluctuation relaxes, the second electron can occur by to lower its energy with the concentration of positive charge. The effective attraction generated by this process is sufficient enough to overcome the force of repulsion between the two electrons. Prolek in 1950 discovers the mechanism of electron-phonon pairing, which was later confirmed by the discovery of isotope effect. Another important term is the Cooper pair. A simple quantum mechanics problem can most efficiently describe the physics involved in the BCS theory. Let V of R1 minus R2 is an attractive potential for the two electron system interacting with each other. The Schrödinger equation for the two-body problem is given as within the brackets minus h cut square del r1 square by 2m minus h cut square del r2 square by 2m plus v of r1 minus r2 brackets close into psi of r1 r2 is equal to e into psi a function of r1 r2. By reducing the two-body problem to one-body problem with the help of the concept of reduced mass, the above equation can be solved to get the wave function psi of R1 R2 and the energy E. Regardless of the amount of attractive interaction, a bound state will be generated from the respective solutions of the wave function and energy. Such a bound state is called a Cooper pair. In case of the free electron, the attractive interaction has to overcome a threshold to create a bound state. Thus, the formation of Cooper pair is fundamentally different from the formation of free electron. The existence of a well-defined Fermi surface is found to be the basic feature which is responsible for different behavior. We will next discuss another term related to the Josephson effect. Josephson junction describes the contact between two superconductors in which there is found to be a thin, less than 2 nanometer dielectric tunnel barrier between the two superconductors. The effect explains the tunneling of Cooper pairs through a barrier. The DC-Josephson effect relates the tunnel current to critical current IC through a Josephson junction as I is equal to IC sin phi. The maximum Josephson tunnel current flowing through the barrier is called the critical current. The value of the tunnel current is measured by the density of Cooper pairs, tunnel barrier thickness, area of the tunnel junction, and by the phase difference phi. The AC-Josephson effect relates the voltage across a junction to the temporal change of the phase difference. Thus, a voltage across a Josephson junction leads to a current. Let us now discuss the microscopic theory, which is the BCS theory of superconductivity. BCS theory is a microscopic theory that should describe the phenomenology of superconducting materials based on first principles, namely electron and crystal structure of the material and Hamiltonian of the system. According to the investigations of this theory, the physical nature of the command parameters should be identified. Special, non-classical features of the superconducting phase should be outlined. The fundamental understanding of superconductivity should not depend on the band structure of material, since the superconductivity is observed in many metals. Also, the theory demands the detailed form of electron-electron and electron lattice interaction. A temperature-dependent description should make use of thermal Green's functions. We will now take up the BCA's many particle state theory. A reduced Hamiltonian is required to find a many particle state. The Hamiltonian is reduced under the considerations of forming the Cooper pairs and respects the Fermi character of the electron. During this process of forming the Hamiltonian, it is taken into account that the structure of the solution is not affected much due to the missing parts of the Hamiltonian, and the contributions in the normal and in the superconducting state is maintained to be same. The variational principle is used to get the correlations in the many particle state. For the application of the principle, we need the matrix elements of the reduced Hamiltonian, and after some tedious algebra, the desired wave function is achieved. We will now discuss the applications of superconducting thin films. One important application of superconducting thin films is maglev trains, which is also referred to as magnetic levitation trains. Since the superconductors repel a magnetic field, therefore, they practically get rid of the frictional effect between the train and the track. However, due to the strong magnetic fields, the safety concerns are there, which leads to a risk to human health. Second important application is in particle accelerators or Large Hadron Colliders. Rutherford Appleton Laboratory in Oxfordshire, UK, developed this use of superconductors in 1960s. By a coalition of scientific organizations from several countries, the biggest Large Hadron Collider is built in Switzerland. In case of accelerators, to accelerate charged particles very fast around the speed of light, extremely powerful electromagnets were developed using superconductors. Another important application of the superconducting devices is in SQUIDs. SQUID stands for Superconducting Quantum Interference Devices. These devices are used to detect very weakest magnetic fields. In mine detection equipments for the removal of landmines, these devices are found to be helpful. The last application which is discussed in this module is the E-bombs. USA is trying to develop these devices by making use of the strong magnetic fields derived by superconducting materials, which creates fast and high intensity electromagnetic pulse to disable electronic equipments of the enemies. In March 2003, wartime E-bombs were first used by USA forces to attack Iraqi broadcast facility. E-bombs can release a huge amount of energy, around 2 billion watts at once. We will now talk of some uses of superconductors which are under development. One of the important ones is the efficient generation of the electricity. Secondly, prompt computing processes are also exploited for the applications of superconductors. Some of the important features of the superconductors are Bose condensation of diagonal long-range order, Meissner effect and flux quantization, Josephson effects, temperature dependence, crystal structure, Fermi surface, and electron-phonon interaction. So students, let us now summarize what we have learned in this module. In this module, the superconducting behavior was discussed in contrast to normal metals. The various properties of superconducting thin films were studied. Phenomenological and theories of superconductivity, London theory and Ginzburg-Landau theory were explained. The important terms related to the superconductivity, such as electron-phonon interaction, Cooper pair, and Josephson effect were studied. Finally, the microscopic theory, that is BCS theory of superconductivity and BCS many particle state theories were discussed. Thank you students for your attention.